Today we get into remainders and error bounds, and these are the things that we leave off of a Taylor polynomial by stopping after a certain number of terms. So if you remember, the formula for a Taylor polynomial goes like this, that some function f of x is going to be f of a, and a is the center of our series, remember, f prime of a, x minus a, plus f double prime of a, x minus a squared over 2 factorial, and because I'm running out of space already, I'll write this as the nth derivative, x minus a to the n over n factorial, plus the remainder when you stop after n terms. So this thing over here is my remainder, or you might also call it my error. In other words, if I stop after only 4 terms of my Taylor polynomial, there's an awful lot that I'm leaving out there, like an infinite number of terms. So the difference between the value of the function and the value of my polynomial approximation, that will be the remainder or the error. Now, there's 2 different forms of the remainder that we're going to look at. The first one, and actually they're very much related to each other. The first one is what we call the LaGrange form of the error bound. Now, look at those words, LaGrange form of the error bound. In other words, I'm coming up with a number that says the error will be no more than this. It doesn't tell me actually what the error is, but it says that the error is bounded by this value, that it will be no more than this bound. Sometimes the bound is very good, sometimes the bound is way off, but in no case is the bound too low. The bound is always an upper bound of the error. Now, the Lagrange form of the error bound looks like this. The remainder by stopping at n terms is going to be the n plus first derivative. So if I stop at 4 terms, I'm looking for the 5th derivative. Evaluated at some constant c, and I'll tell you about that in a minute, times x minus a to the n plus 1 over n plus 1 factorial. Now, we choose a c that is what we think of as the worst case. Because if we want an error bound, we want to make sure that we don't find a value that's too low. We want to pick a c value that makes it what we think of as the worst case, so that we come up with a true bound, and it's not any more than that. All right, so let's look at an example and see how this works. Let's take a look at a cubic polynomial. All right, so let's look at let's do a second degree polynomial. We'll do it for the cube root of x. I don't feel like finding that extra term. So let's do f of x equals the cube root of x. We'll do a polynomial of degree 2 centered at a equals 8. And then from there, I'll ask you questions about error bound. So the first thing is, let's find that polynomial first. So f of x equals the cube root of x, which is x to the 1/3 power. If I derive the cube root of x, right, so if I derive x to the 1/3, I'll get 1/3 x to the negative 2/3. So 1/3, and x to the negative 2/3 is the same thing as the cube root of x squared. Okay. If I'm going to talk about error bounds, I'm going to need one derivative more than the degree of my polynomial. So while I'm deriving here, let's just keep going. All right, so if I have over here x to the 1/3, the first derivative is 1/3 x to the negative 2/3. The next one is going to be negative 2/9 x to the negative 5/3. And so if I want to write that as a fraction, I'll get negative 2 on the top, and then 9. Let's see, x to the 5/3 is the same thing as x cube root of x squared, right? That's x to the 2/3. That's x to the 3/3. 3/3 plus 2/3 is 5/3. And then the third derivative I'm going to find because I'm going to need in a minute, not immediately, but while I'm on the track of deriving, let's do it one more time. 5 times 2 is 10, 3 times 9 is 27, 2 negatives make a positive, so there's my coefficient. It'll end up being x to the negative 8/3. All right, so this one will end up being 10 over 27 x to the 8/3. All right, to build this polynomial, I really don't need anything but the first 3 derivatives, so let's evaluate f of 8. F of 8 is the cube root of 8. Cube root of 8 is 2. Okay. F prime of 8 is going to be 1 over 3 times the cube root of 64, right? 8 squared is 64. Lucky for us, the cube root of 64 is exactly 4. 3 times 4 is 12. Okay. F triple prime, or F double prime of 8 is going to be negative 2 over 9 times 8 times 4, right? Again, the cube root of x squared, 8 squared is 64. The cube root of 64 is 4. All right, so if I multiply 9 times 8 times, I'll do 2 because I'm going to cancel it out with what's on the top. I end up with a negative 1 over 144 if I simplify. All right, so what does this polynomial look like? It's going to be f of a, which is 2, plus f prime of a, x minus a, plus f double prime of a, x minus a squared over 2 factorial. All right, let's move that all up a little bit, and we claim that the cube root of x is approximately 2 plus x minus 8 over 12, and then minus x minus 8 squared over 288, right? 144 times 2 is 288. All right, so now here's my question. How accurate is this on the interval from 7 to 9? And notice that this one happens to be centered at 8, and so the interval that I'm looking at is symmetric. That doesn't mean that it's going to have the same amount of error on both sides. It just means that the interval that I'm looking at is symmetric. All right. If I go to my error formula, the error formula asks for the n plus first derivative, right? So the remainder, LaGrange form of the remainder, says that if I stop after n terms, I need the n plus first derivative. So if I stop after 2 terms, the remainder for stopping after 2 terms is going to be the third derivative at some c value, x minus a, which in this case is 8, to the n plus 1 over n plus 1 factorial. So right away I filled in a few numbers, right? If I stop after 2 terms, then my n plus 1 becomes a 3. I need a third derivative, and those numbers always match up. The third derivative, the third power, 3 factorial. All right, so now I need to choose 2 values. I need to choose a c value, and I need to choose an x value. Well, at the end of the day, really what we're looking for is absolute values. So if you look at the interval from 7 to 9, what will make this thing the biggest? It doesn't matter, actually, whether I put a 7 or a 9 in there, because 9 minus 8 is 1. 7 minus 8 is negative 1, but when you take the absolute value, you still get 1. If I put any other number in there besides 7 or 9, I'm going to get smaller and smaller values. So let's assign let's assign x to 9. Now we've got to figure out what to do with that c value. Look up on the top here. That third derivative is still over here. Now in this case, it matters whether I put in a c equals 7 or I put a c equals 9. The bigger the number in the denominator, the smaller the value of f triple prime. So I would like to put the smallest value possible into that denominator. So out of the 2, between choosing a 7 and choosing a 9, I'll choose c equals 7 because it makes the third derivative larger. Okay? Sometimes it doesn't make a difference, but in this case, actually putting a 7 in is a different answer than putting in a 9. So when I calculate this, that third derivative, f triple prime of 7, will give me 10 over 27 times 7 to the 8/3 power. Okay, let's assemble that and see what number I get. I claim that the remainder, stopping at 2 terms, is 10/27 and then 7 to the 8/3 times 1 to the 3rd over 3 factorial. Now I'm going to go ahead and get a decimal approximation because I have no clue what that number is. off the top of my head. Right? If I do 10 divided by 27 times 7, hit the up arrow key, and then in parentheses put the 8/3 power and close your parentheses. Now take that number and divide it by 6. Here's the number that I get. I get 0.000344. Okay. What do I claim? I claim that that number tells me that on the interval from 7 to 9, that will be the maximum error. Is it the actual error? No. The actual error could be less than that, but that's the maximum error. So what did I do? I took my remainder, LaGrange form of the remainder bound, which was this guy up here, right? It's the n plus first derivative. You've got to pick the c, right? You got to pick the c to be left or right, or actually it could be in the center of the series as well. X minus a to the n plus 1, n plus 1 factorial. All right. How good is that error bound? Well, let's find out. And here's how we're going to find out. I'm going to sketch this here for a second, then I'm going to go over to Desmo and type it in for you. I want to find out the difference between the cube root of x and the polynomial on the interval from 7 to 9, and I want that difference to be the absolute value of the difference. In other words, I don't care if it's above or below. I just want to know how far off it is. All right, so let's try this out and see what we get. I'm going to have to play around with windows a little bit here in order to make this make any kind of sense. So let's start with y equals the cube root of x. I'll type it in as x to the 1/3. Okay. Then my second one will be the polynomial. So y equals 2 plus x minus 8 over 12 minus x minus 8 squared over 144. Okay. Down the bottom, actually, let me call this f of x. And I'm going to call the other one g of x because then it makes it a lot easier. Let's deselect these two things. And down the bottom here, I'll write h of x equals the absolute value of f of x minus g of x. All right, so I've got x to the 1/3. Then I've got my polynomial down here, 2 plus 1/12 times x minus 8 to the first minus x minus 8 squared over, actually I think this should be here. Let's go back and look. I'm doing this off memory, and memory is not doing well. Okay, it should be 288. All right, and now I'm going to look at the absolute value of f of x minus g of x. So I want to look at the difference between the cube root of x and the Taylor polynomial that I've come up with, and I want it on the interval between 7 and 9. Remember, our original question was, what is the error on the interval between 7 and 9? Well, if I scroll all the way out here between 7 and 9, it doesn't look like much, does it? Let's go back to those numbers that we came up with. We said we wanted the x values to be between 7 and 9. So let's look at values only between 7 and 9. And we said that the maximum error was 0.000344. So let's make this go up to 0.0004. Ah, okay. There's a graph of my error. Notice how incrementally small this is, 0.00005. So this is really tiny error. Notice down here at the bottom, I don't even know if you can see this. I'm going to move this up. There we go. All the way down the bottom here at x equals 8, the error is sitting on the axis because the axis is 0. So there is 0 error at x equals 8 because that's the center of the series. So way back when we said that one of the things the Taylor series can do is it can converge only at its center. And there is no option for it to not converge. So everything has to converge at least at its center. And here you can see that the error is actually 0. Take a look at the two sides of this, right? The right-hand side has a little bit less error than the left-hand side. The left-hand side is a little bit higher. The right-hand side is a little bit lower. So when we picked the C value to be on the left-hand side, we were correct in saying that there's more error on the left side of this than there is on the right side. What was the error that we came up with? We came up with a bound of 0.000344. All right, well, that's not terribly off, right? That red line up at the top is 0.000344, and it's clearly a bound. It doesn't get any higher than that. Is it exactly the error that's the maximum? No. The maximum error is closer to 0.0002627, somewhere in there. But yet our error bound served us well, right? It told us that the error is no more than 0.000344. All right, let's take a look at another one. Let's take a look at one that involves a natural log, and we'll come back and we'll try to do the same thing by graphing. So the actual error is closer to 0.00026 or 27, but our approximation, our error bound, was not wrong, right? It's still a bound. So now let's look at the formula for the natural log of x. All right, so I'm going to tell you that the natural log of x can be represented as x minus 1 minus x minus 1 squared over 2 plus x minus 1 to the third over 3. So there's a third degree Taylor polynomial for the natural log of x. And I want to estimate the remainder, find an upper bound for the error, or for the remainder, on the interval from 0.7 to 1.3. So you can see that the series is centered at 1. All right, so this is a symmetric interval around x equals 1. All right, what do we need for an upper bound for error? Well, in this case, what I'm really looking for is the remainder after 3 terms. And again, for this, I'm going to use the LaGrange form of the error bound and see if that leads me anywhere. So the remainder after 3 terms is going to be the n plus first derivative, so that would be the fourth derivative evaluated at some c value, times x minus 1 to the fourth over 4 factorial. And again, I'm looking for absolute values, so it actually doesn't matter whether I put the 0.7 or the 1.3. And actually, that fourth power on top of it will take care of it for me, because if I put a 0.7 in, I get a negative. Raise it to the fourth power, now I get a positive. So let's use x equals 1.3. Now, for the fourth derivative, I'm actually going to need a fourth derivative. So let's evaluate it. If f of x is the natural log of x, I'm going to be a little cheap here. F prime of x then is 1 over x. F double prime is negative 1 over x squared. F triple prime would be negative 2 over x to the third. And so the fourth derivative would be positive 6 over x to the fourth. Right? Did I get those signs right? No, because that one was negative, and this one should be positive. And that one should be negative. Okay, so I get negative 6 over x to the fourth. That's the fourth derivative. Now, here's my goal. I want to find the maximum value of negative 6 over x to the fourth on the interval from 0.7 to 1.3. Now, we can still think of it as finding that c value, right? What is the c value that makes it the largest? Well, the largest c value is going to come from which end of that interval? It's not going to come from 1, right? 1 is the middle. That would give me a value of 6. If I put a smaller value in for the denominator, that should make the value of the whole fraction larger. If I put a bigger number in for the denominator, that's going to make it smaller. So let's choose c equal to 0.7. Right? So if I put the smaller number in, that'll make it larger. So we're going to look at negative 6 over 0.7 to the fourth and see what we get. 6 divided by 0.7 to the fourth gives me 24.99. That's a pretty big number. Keep in the back of your head what we're doing here. I'm finding the maximum value of negative 6 over x to the fourth on that interval. All right, let's throw it into the formula. Right? There's our red formula up at the top. This thing over here is our 24.99. So I got 24.99. That's the maximum value of that fourth derivative. We said we're going to put a 1.3 in for x. So 1.3 minus 1 to the fourth over 4 factorial. That's going to give me 24.99 times 0.3 to the fourth over 24. And then that's just left for us to throw into a calculator and see what we get. 0.3 to the fourth. Take that, multiply it by 24.99, and then divide that by 24. I get 0.00843. Okay, that's my error bound. My claim is that the maximum error on that natural log function between 0.7 and 1.3 will never exceed 0.00843. Okay, let's see if I'm right. So I'm going to go back to trusty old Desmo, so I'm going to get rid of everything that I have. I could have left that 1 in there. Yeah, that's all right. All right, so just so you can see what I'm typing in here. I get y equals the natural log of x. The second one, actually, let's call this f of x. Then g of x will be my polynomial approximation. So it'll be x minus 1. And then minus x minus 1 squared over 2 plus x minus 1 to the third over 3. All right, so that's my third degree Taylor approximation for the natural log. There's g of x, f of x, and now h of x will be the absolute value of the difference. I'm going to get rid of the other two because I really don't need them. And now we need some windows. Okay, what window settings am I going to use? We wanted to know how this behaves between 0.7 and 1.3. So the one we had for the last problem is a terrible window. So let's make this go from x equals 0.7 to x equals 1.3. And we also said that the maximum error that it gave us was 0.00843. Well, where is my error graph now? My error graph is way down the bottom of that screen, which means that that error bound was really, really high. How high? Well, the actual error looks like it's about 0.002 something, 246, maybe 0.26, 0027, somewhere in there. It's clearly not up on the top, right at the top. That top line is the error that we came out with from the LaGrange form of the error bound. That is way above the actual error for this natural log function. And the fact that I was putting in a value on the bottom that was a fraction, I was raising it to the fourth power, I ended up with a very large value at the beginning there. That's why the error is so off. So it's not that this failed us, right? It's not that we came up with an error that was more than the error bound. The error bound worked just fine in saying that this is the maximum error. However, it's clearly a much higher error bound than the actual error for the graph. All right, keep in mind the little thing we did before where I said we're going to take a c-value to find the maximum error. Keep that terminology in mind because in a minute we're going to use that to come up with a new way to find the errors.